Welcome everyone to the first of our Michelson Postdoctoral Prize Lectureship lectures for this year. So I'm very happy to introduce the winner for this year, Ben Lehman. So Ben is a native of the Bay Area. So he did his undergrad at Stanford, he did his PhD at Santa Cruz, and now he's a Pappalardo Fellow at MIT. And he's works on all things dark matter, which he's going to tell us about today. And then the second lecture is tomorrow at 11:30, same room. And then we have the colloquium at the usual time at 4 on Thursday. And then on Wednesday, we also have a special reception at 4:30, which will also be here. So we look forward to all those events. And Ben will be here and around all week. And there's plenty of opportunity to meet with him and to interact with him. So please take advantage of that. So without further ado, I'll turn it over to Ben. And don't forget, if you want to ask a question, it's being recorded, so grab the microphone.
Thank you, Kurt. It's such a pleasure to be here and to put a lot of faces to a lot of names. I have the rare pleasure of being able to talk at length about a lot of different subjects within dark matter physics that make me excited. I am going to treat this and tomorrow's talk as indeed technical talks, so I am not going to give quite as much background as I intend to give on Thursday. So if dark matter is not what you think about all day, and there's something that's a little bit unfamiliar, of course, I'm happy to answer questions, but also bear in mind that on Thursday I'm going to try to put some of these threads together. So what I want to focus on for this first talk is really about direct searches for dark matter. Dark matter is something that we look for in many different ways. I'm going to talk about several different ways that we are trying to pin down what it is. But for the purposes of this talk, I want to focus on just one strategy, which is looking for dark matter particles in the lab. And I want to give you a sense of some of the recent progress over the past couple of years and the path for us to really flesh out the promise of dark matter detection in the coming 5 to 10 years. So just to give you a little bit of context, if we're going to talk about dark matter, which underlies most of the matter in the universe, we know a lot about it. We can make beautiful pictures of its structure in computer simulations. What is it? Well, you can't talk about the nature of dark matter without talking about the elephant in the room, which are WIMPs, weakly interacting massive particles. This was the single motivating influence that dominated the dark matter phenomenology world for many years, I would say 30 or 40 years. An exceptionally well-motivated paradigm. And just to kind of highlight where the WIMP paradigm took us over the last few decades, I want to show you this review that came out a little while ago. I'm just going to read for you the last line of this review. It says, "The moment of truth has come for WIMPs. Either we will discover them in the next 5 to 10 years, or we will witness their inevitable decline." Well, now I can tell you that that paper was actually 10 years ago, and there are no WIMPs yet. So now we see titles more like this. Now, I don't want to undermine the WIMP as a dark matter candidate. There's actually still really interesting parameter space to explore. There's a really interesting experimental program. And I actually kind of want to use the WIMP as motivation, because we have actually used that theory space target to develop an enormous program, both in theory and experiment, that has allowed us to make very concise conclusions about what kinds of WIMPs can and can't make up dark matter. So now that we are sort of in the post-WIMP era and everyone in the dark matter world is thinking about what else we could be looking for, I want to suggest to you there are really two strategies. One is model-driven in the same sense as WIMPs, where we say we have a really good idea for what dark matter could be that's very well motivated. Let's go and explore that. Or we could take a model-independent approach, where we develop probes that are sensitive to lots of different kinds of dark matter phenomenology. We use those broadly. We see what we learn. Now, I'm actually going to argue for using both of these. And the reason that we have to use both of these is because of what we're up against, which, just to give you a sense, is this line. This is one slice through the dark matter parameter space in mass. There's 90 orders of magnitude here, so we're not doing too well. We have spent most of the last 40 years probing a subset of that red band. So where do we go from here? Well, what I'm going to do in this talk is actually focus on this yellow band, what I'm going to call light dark matter. This is dark matter between about the keV scale and the GeV scale. What's exciting about that parameter space is that not only are there reasonable, well-defined models that we can go and look for in this space, but it's actually also possible with sort of simple extensions of the same kind of searching we've done already for WIMPs. We can extend those techniques to go down those remaining orders of magnitude and actually capture a reasonable parameter space where we think dark matter can live. So here's what I want to do in the rest of this talk. First, I want to explain how, in going to those lower dark matter masses, we actually can take advantage of condensed matter physics. And I'm going to tell you about how dark matter interacts in condensed matter systems. Then I want to show you how we can actually use the frameworks that have been developed in the condensed matter and material science worlds to actually take advantage of vast data sets, to actually design better dark matter detectors that can really be implemented. And because they can really be implemented, and I have wonderful experimental collaborators who go and build these things, I can actually show you some prototype results from real dark matter searches that were implemented in the lab, demonstrating the ideas that I'm going to tell you about, and I'm going to show you the things that we learned as we designed those experiments. So, to get started, I want to give you a little bit of context on how searching for this lighter dark matter works. And we should start with the plot that you get from every direct detection experiment. This is a result plot for limits on dark matter from a laboratory experiment. The horizontal axis is the dark matter mass. The vertical axis is the cross-section. So you want to be lower in this plane. And you'll notice that the curves all kind of swoop up and die off at low masses. That's kinematics. This is just the fact that when the dark matter mass becomes lighter than the mass of the target that it's scattering with, it can no longer exchange energy efficiently, and so you lose sensitivity. Now you'll notice this happens around 10 GeV. That's not a coincidence. This is because this is a detector. These are detectors that are built using atomic nuclei. So those have GeV scale masses, and if I have a nucleus that has a 10 GeV mass, I should expect to be able to probe dark matter masses as low as 10 GeV. Now we thought that was fine for looking for dark matter as a WIMP, because WIMPs are associated with the electroweak scale, which is up at hundreds of GeV. But now that we want to go lower, let's think about how far down we actually want to go. Well, I'm going to suggest that we really want to go down about 6 orders of magnitude. And it's not just because of the models that live in those 6 orders of magnitude. It's because there's a floor 6 orders of magnitude down from the GeV scale. At the keV scale, there are substantial constraints from cosmology that tell you that dark matter cannot be a fermion below the keV scale. So if you build experiments that are sensitive to dark matter fermions down to the keV scale, you have made qualitative progress. You can make an actual statement about what dark matter is or is not. Now, of course, dark matter could be a boson, in which case it could be lighter than the keV scale. As it turns out, there's sort of a lucky coincidence here that if dark matter is bosonic, but still particle-like, not overlapping and wave-like, then these bosons have to be at least about a millieV in mass. And it turns out, for reasons I'll explain, that any experiment you build that can probe keV scale fermions can also probe millieV scale bosons. So this is really the future of direct detection summarized. This is the challenge. We have to get down to the keV scale for fermions. If we do that, direct detection has sort of reached its natural limit as a platform for dark matter detection, for dark matter science. Now, how are we going to do that? Well, one really easy thing you could do, if we're being limited by the kinematics, by the mass of the target, we could swap out a lighter target. So we could think about dark matter scattering with electrons, which are MeV scale. And indeed, if you do that, and you look for dark matter scattering in existing electronic detectors, you already get limits that go down in mass down to the MeV scale. They're not quite at the scale, they're not sized up now to the point where you can really probe interesting cosmological targets, but they're getting there. In fact, in some portions of the parameter space, those have been probed. Now, here's the issue. If you want to take this concept and go those last 3 orders of magnitude down to the keV scale, now you have a problem. Because dark matter scattering cannot be considered as free particle 2-to-2 scattering anymore. Now you are at energy scales that are also controlling the condensed matter physics of the material, and so you are sensitive to the condensed matter physics of the material. Now, arguably this is a giant mess, because that means that you're now sensitive to all the eigenstates of the detector, right? You don't actually know what the scattering process is in clean language. All you know is that the detector has two eigenstates. The dark matter is enabling a transition between those two eigenstates that could be very complicated. How am I supposed to make a prediction now? How am I supposed to know what kind of experiment is appropriate? I notice that you're looking through me, so I'm going to move over here. How about that? Better?
Either way is fine.
Okay.
Wait.
Okay.
No, Kurt's just looking for you.
Okay. Kurt, I don't care about. All right. So I'm actually going to argue that this is a huge opportunity for us. Because if we can actually understand what sets those detector eigenstates and understand how to engineer detectors that have favorable eigenstates, we can build really sensitive experiments that can do amazing things. So here's how we can do it. Let me tell you about how dark matter actually interacts in condensed matter systems. And the idea here is actually really simple. Let's just start by separating the probe, the potential that is actually mediating the interaction, from the response of the detector system. So in a perfect world, I would have the dark matter coming in and leaving, some function that describes the interaction between the dark matter and the system, and a totally different function that characterizes the response of that system that knows about all the eigenstates of that system. So if you walk down the hall and you ask your condensed matter friends, they might notice that I've chosen the letter epsilon here, which is not coincidental. In fact, the response function for this purpose turns out to be the ordinary dielectric function of the material. So if you know the dielectric function, it turns out you know everything about how dark matter scatters in that system, modulo a few caveats. So here, when I say dielectric function, I literally mean the ratio of applied potential to total potential in the material. This is just electrons responding in the same way that they do to an applied E field. I've just written it in Fourier space, so you have Q as momentum transfer and omega as energy transfer. And it turns out that a lot of the phenomenology that you are already familiar with from ordinary E&M applies directly to dark matter interactions. So, for example, you're familiar with screening, the idea that if I put an E field on a conductor, then the electrons will rearrange themselves so they'll cancel out that applied potential. The same exact thing happens with dark matter scattering. I'm going to show you an example of that. All right. Given that fact, it turns out, I'm going to skip a few steps here, you can write down the dark matter interaction rate in terms of two quantities. In red, that's the interaction potential. That's where the particle physics lives. In blue is the loss function, or energy loss function, the imaginary part of -1 over epsilon. That characterizes everything about the material response, and it tells you what the scattering rate will be. Now, there are a bunch of advantages to working in this language. I'm just going to list a couple. First of all, in this framework, the dark matter interaction rate is easily predictable. Right? So there are already plenty of ways to estimate the dielectric function of a material, and so you can use that now to directly estimate the dark matter interaction rate in a material. You can also use this in an empirical way that's data-driven. So because it's the same dielectric function that mediates the dark matter interaction rate and standard model interaction rates, I can go and shoot electrons at a material, measure its dielectric response, and then use that to calibrate a dark matter experiment. It's also naturally anisotropic. I'm going to explain in a moment why that is so important. But what this means is that you can actually use this framework to build directionally sensitive experiments, which is absolutely crucial for background rejection. So actually, why is it so crucial for background rejection? So we live in a galaxy that is sitting inside a dark matter halo. We don't sit at the center of this galaxy. We sit somewhere on an arm. And as we rotate through the galaxy, that means that there is a preferred direction for dark matter to come through our frame. There's a dark matter wind that we experience. So if we are if we have an experiment that has directional sensitivity to the direction of the incoming dark matter, we know exactly where it should be coming from. And that means that we can reject any background that isn't coming from the correct direction. The way that we usually phrase this in the dark matter literature is in terms of a daily modulation, which means that as Earth rotates, if I have an experiment that's sitting on the table, Earth is going to expose a different side of that experiment to that dark matter wind. So if the experiment has a different sensitivity in different directions, I'll see a wiggle in the event rate as a day goes on. But I think it's really, really important to be clear about two things. First of all, that this is the only way that you can actually hope to find a signal or even set constraints in this low mass regime. Because we are not going to be able to do the same enormous effort of eliminating backgrounds that was done for the large WIMP experiments. That took many, many years and many millions of dollars. So having anisotropy is a much, much more effective tool for the next generation of experiments. The other thing that I want to make clear is that even though I'm going to use the words daily modulation, it's a term of art. It's only a way of quantifying. It's a figure of merit. It really is not just daily modulation. It's really directional modulation. And the reason I want to make this so clear is because if I just said, okay, I'm going to look for a daily modulation, you might say, well, couldn't you do the same thing on the basis of a year? As Earth's position changes from side to side of the sun, we're moving with or moving away from the velocity through the galaxy? Well, yes, and in fact, this was done. So there were, for a long time, there was this idea, the right way to look for a dark matter signal is to look for a little enhancement that should come up from the enhanced density that we see as the Earth is following the direction of our motion through the galaxy. And in fact, there is a famous experiment that found such an annual modulation. This is called the Dama experiment. Now, unfortunately, that Dama result, although at many, many, many sigma, a detection of dark matter, has not been reproduced by other experiments. And we don't really know exactly what the source of that signal is, but there are lots of things that can vary on a year-long time scale. So I'm not saying that I'm going to see a signal that varies on the course of a day, therefore it's dark matter. There are other things that vary on the course of a day, like the sun. So instead, what I want to make clear here is that if I have directional sensitivity, I can actually say the dark matter signal comes from that direction in the sky. So as a concrete example of this, I could take two detectors, point them in different directions, run them at the same time, and I should see a phase delay between those two detectors' rates. Nothing to do with daily modulation, everything to do with directional modulation. Okay? All right. Now, let me give you a quick overview of what we can say about that dielectric function. Even though it's familiar from ordinary E&M, you probably aren't used to seeing it in this Fourier transformed language. So it turns out you can actually compute the dielectric function analytically under a certain set of assumptions. It turns out to be related to the susceptibility. So it's really just a linear response function for perturbations to the electron density. I can write it in terms of this chi, this linear response function, just by factoring out the Coulomb potential. So I'm going to work equivalently with inverse epsilon or with chi. The only difference is this Coulomb potential. And it turns out that chi can be written as a correlation function. And now you can go and use your favorite techniques from particle physics, condensed matter physics to compute that correlation function. In fact, you can do it diagrammatically. You can write down the set of diagrams that contribute to that correlator. You can evaluate them at any loop order that you like, and you can write down the resulting dielectric function. Now, as it turns out, there is an approximation which is going to be really useful for understanding the phenomenology here. So ordinarily, if I were to try to compute all of these diagrams, I would find the one particle irreducible diagrams, the ones that I can't just cut them into two diagrams by snipping one line, and then I would do a geometric sum over all the different copies of those diagrams. The simple approximation is to say the only one particle irreducible diagram is that one, P1. I'm going to ignore all of these fancy diagrams. I'm only going to consider a number of insertions of P1. So in diagrammatic language, I have one bubble plus two bubbles plus three bubbles, etc. If I do that, this corresponds to what is known in the condensed matter literature as the random phase approximation, and it gives rise to what's called the Lindhard dielectric function, which, even though it's ugly, can be written down explicitly. I'm going to show it to you in closed form. It looks like this. It's a little nasty. It's a log, a bunch of logs, imaginary parts. It's easy to actually mess up which branch of the log you take, but there's a couple of things I want to point out. First of all, it's completely closed form, completely analytical, and there are a couple of scales that have shown up now. These correspond to material parameters. So there is now a plasma frequency, omega p, that's going to end up corresponding to a resonance. It is typically of order the Fermi energy in the material. And then there is this gamma parameter that you see in red that always comes together with omega, the energy. So that is actually the width of that resonance. That turns out usually to be somewhat smaller, so these are usually narrow resonances, although not always. So we now have a sense that there's a resonance. That's nice. I want to come back to the intuition that you already have for dielectric response. And in particular, I promised I would show you what screening looks like for dark matter. So let me show you this comparison between two different projections for direct detection experiments. Remember, lower is better in this plot. Dark matter masses on the horizontal axis, cross-section on the vertical axis. Now, in the literature, some years ago, a projection appeared that looked like the dashed purple line. That was done using ordinary, just pre-particle scattering, no account of the material eigenstates. What you get when you actually use the Lindhard dielectric function is the orange line. That's 12 orders of magnitude of difference at those lowest masses that we care about. So this is tremendously consequential, but what's actually going on here is exactly the dark matter analog of screening. That the dark matter is effectively applying a potential to the material. The electrons are rearranging to cancel out that applied potential. So you end up with a suppression at low dark matter masses. Now, incidentally, there's actually a really interesting technical fact that comes out of this. Because you might have thought, if you were thinking in sort of free particle language, that you might have predicted this if the dark matter interacts via a vector mediator. Why a vector? Because vectors can mix with the photon in medium. And we know photons are screened. So if I have dark matter coming in, it has a vector mediator come out, that vector mediator mixes, the photon is screened in medium, I should expect a screening for the dark matter interaction. But then why should a scalar be screened? Surely if I have a scalar mediator, that wouldn't be screened. But it is, because the screening is entirely a property of the material response. It has nothing to do with what is mediating that interaction. And in fact, you can show with a lot of elbow grease why, in fact, scalar mediators are screened to exactly the same extent as vector mediators. It is possible to do. It's much easier to just say, I know why. It's because it's not a property of the mediator. It's a property of the response function. Please.
Can I ask a quick question?
Yes.
Why is that, I'm from condensed matter physics, by the way, but why would a dark matter particle produce a screening electric response if it doesn't have a charge?
Good. So effectively, you should think about the dark matter in these scenarios as having an effective charge, right? Like it's coupled to the electrons in some way. Right? So one of the ways to do that is indeed by giving it a millicharge. There are lots of different interaction structures, some of which do or don't look exactly like an electric charge. The assumption that I'm actually making here is that the coupling is to the electron number density operator. So there is some coupling that you're probing. Now, but because you're coming from the condensed matter side, I want to also emphasize here that the size of that coupling is not arbitrary. There's a reason to pick a particular coupling, and that has to do with making the dark matter have the appropriate abundance. We know how much dark matter there is, and we know that it can be produced in the early universe if it has a coupling to standard model particles. So knowing how much dark matter there is, if I say it interacts with electrons, and I know the mass of the dark matter, I know immediately what should the coupling be in order to give me the appropriate dark matter abundance, and that's what I go look for.
Thank you.
I Just wanted to jump on that and ask another question, also from the non-particle physics side. So you said, WIMPs are out, maybe, and that those ones are like weekly. Okay. I don't mean to start a controversy, but the idea there, those interact via the weak interaction, and these are not. These are some new hypothesized interaction that we don't know about.
I'll say more about this on Thursday. The thing I'll say for right now is that WIMP is actually a deeply overloaded term that can mean many things to different people. They are certainly not all the way ruled out. It does not necessarily mean that it interacts via the electroweak force. That is one class of WIMP dark matter. So generically here, I'm thinking about a totally different interaction structure. So the kind of interaction that, like what I described here, where you couple directly to the electron number density, that is actually something that will come out in the non-relativistic limit, which is where we're living here, for basically like any scalar or vector mediator. Anything that's not spin dependent, pretty much, will end up giving you this interaction in the non-relativistic limit. Other questions? All right. So hopefully now I've depressed you by showing you that screening ruins your dark matter experiment. So now I want to revive our spirits a little bit. There are also condensed matter effects that can help us build better dark matter experiments. And here I want to start with plasmons. So what is a plasmon? If you Google it, as I once did, you will find out that it is a brand of biscuits for babies in Italy. I believe Catherine Zurich feeds these to her kids. It's also part of our proud tradition of naming particles out of things we discover on the shelf. But really, what is a plasmon? A plasmon is a collective mode in the electron system. So at the cartoon level, you can think about it as electrons sloshing back and forth together. And there's particular scale in a given material or condensed matter system for where that is resonant. And if I actually look at the loss function, the imaginary part of negative 1 over epsilon, for a real material, I will actually see this as a resonance. So here is the loss function of aluminum being fit with an analytical function. And you can see it has this nice sharp peak around 15 eV. That is the plasmon in aluminum. Well, the dark matter scattering rate is directly proportional to this object under an integral. So the bigger this is, the better for us. So this is potentially interesting. Now, I should point out, you might argue, this plasmon is sitting here at 15 eV. Is that relevant for us? We want to probe keV scale dark matter. keV dark matter, moving at 10 to the minus 3 times the speed of light, has millieV energy. That, by the way, is why you can also probe those light bosons. So, millieV energy is much, much smaller than tens of eV. Is this ever relevant for light dark matter? As it turns out, it can be, in part because there are some plasmons in some materials that just lie much lower. There are resonances that one can take advantage of. Also because the plasmons can be quite wide. These resonances are not infinitely narrow. So if I look here at a few different widths for the plasmon in the Lindhard dielectric function, what I'll see is that if the width is narrow, like in the blue curve, the plasmon is only important up at higher energies, and then other physics takes over at lower energies. But if I have a large width, like in the green curve, then the plasmon can actually dominate to lower dark matter masses and lower energy transfers. So it can be important even if the peak of the plasmon is quite high. Okay, quick summary of what we've learned from this Lindhard picture. First of all, screening is generic. It's not model dependent, and we understand why. Second, we have available to us these resonances, these plasmons. And third, the plasmon width can be particularly important for light dark matter. So now what I want to do is I want to take this information that we've gathered and think about how do we design a better dark matter experiment? How do we understand where things are sensitive? So let's do that. This, right out of the gate. This is the Lindhard dielectric function for something aluminum-like. And it looks very messy as a contour plot in momentum and energy. I'm going to break this up for you into a cartoon. So here's the cartoon version of the same thing. Horizontal axis is momentum transfer, vertical axis is energy transfer, and the only thing I want you to pay attention to first are these three wedges. These are the regions of this phase space that are kinematically accessible to the dark matter. Because dark matter has a certain speed that we know, so that means that given a certain mass, there is a relation between its energy and momentum. Now, what we would like to do is basically move as much of the weight in the loss function into these wedges. That is what corresponds to a sensitive experiment. And you'll notice there are two components to the loss function. One is this gray band up here. That's electron hole excitations. And then there's the plasmon. Here it's the blue band. So the big peak I showed you before, that was a vertical slice through this plane, right, at one momentum transfer. So it gave us nice peak shape. And the plasmon actually is there as a resonance for a large range of momenta. But you can see it's sort of frustratingly close to leaking into the dark matter accessible region, right? That place right there where the plasmon almost makes it in to where dark matter can reach, but not quite. So let's try to understand what could we do to find a material, find a system that has a plasmon that would actually be accessible. Well, as it turns out, this is actually a pretty easy exercise. You can write down pretty easily where that plasmon resonance extends in momentum. You can also really simply write down the top edge of these wedges. You put those together algebraically, you find that there's a very simple condition. To access the plasmon, the Fermi velocity in the material needs to be lower than the dark matter velocity. And you can actually do the same exercise with the other piece of the loss function, the electron hole contribution. It turns out that to hit the peak of that distribution, you have the same condition. So finding a target with a low Fermi velocity seems like the thing to do. It's a bit unfortunate, though, that dark matter's velocity in our galaxy is of order 10 to the minus 3 times the speed of light. Typical Fermi velocities are somewhat higher. So you need something a little bit unusual. Well, one way to do this would be to have a material where the effective electron mass is set by material effects, a heavy fermion material, so that at a given Fermi momentum, the effective Fermi velocity is lower. Let's see what that does. So now I can tell you about the last colored piece of this image, the one I didn't call out before, the orange band. That is the plasmon in a heavy fermion material. Specifically, that's uranium ruthenium silicide. And you can see it's now firmly accessible to that low mass dark matter. So if I actually go and draw projections for experiments built out of various materials, I want you to pay attention first just to the orange line, only the orange line. That's aluminum. This is the projected reach for an experiment made with aluminum. You can see it's one of the flagship materials in this parameter space. Now look at the green line. That's the uranium ruthenium silicide. If you started up at a GeV at the right side of the plot, you would say this material is hopeless. It is underperforming aluminum by many orders of magnitude. And yet, when the dark matter mass is around 10 keV, the uranium ruthenium silicide has a plasmon in play and aluminum doesn't. And so the uranium ruthenium silicide wins. Now, I'm not suggesting that we should build an experiment out of uranium ruthenium silicide. Actually, though there are many good reasons, can anyone think of one good reason not to build an experiment out of uranium ruthenium silicide? I take it you can. Okay, indeed, so uranium ruthenium silicide is just one easy example of a heavy fermion material, but the same logic actually lets us do a lot of other detector physics. So what I want to do now is explain how we can now take things we know about real materials and actually find the right materials to design the most sensitive detectors. So here, the heavy fermion thing. This is really nice. Maybe there's something else we can do with it that's more easily realizable. In fact, there is. What if we had this heavy fermion enhancement only in one direction? That is, what if we had a material whose electronic structure is such that the effective mass is different in one direction versus another? That would mean that you would have a different scattering rate in one direction versus another, which gives you a directionally sensitive experiment, the holy grail of background projection. Now, here's how I want to model this. I'm just going to rederive the Lindhard function, but now assuming that I have an anisotropic effective electron mass. And if I look for materials that have anisotropic effective electron masses, there are plenty. So black phosphorus, for example, this is a very common material, easy to use. It has an anisotropy of a factor of 9 between its heavy direction and its light direction. There's even more extreme ratios that you can find easily. So for example, bismuth has a ratio of order 200. Now, how does that actually translate to anisotropy in the scattering rate? Well, if I do this calculation, if I derive the Lindhard function, I can now just sub in, I'm going to skip through the algebra here, you can let me know if you're interested. I can basically just sub in the dispersion relation of a anisotropic mass tensor. I can do a little trick where I do a transformation in the coordinates, and I can show, I'm just going to jump to the punchline here. It turns out the effective linear response function is literally the same as the single bubble bare response function from ordinary Lindhard, except with a transformed momentum. I compute that object, I go through the geometric sum, I get the anisotropic response function. And I can immediately use this to show that indeed, it looks like I have a plasmon that sits in two different places in two different directions. So in the heavy direction here, the plasmon, the dashed one, would be accessible to the dark matter. The light direction plasmon, which is the solid line, would be inaccessible. So you would expect an enhancement relative. Please.
Where's the? Thanks. So in the world of optics, right, if you were trying to kind of engineer a dielectric function, I think one natural thing would not be to use a homogeneous material, but to maybe have like a stack of.
Hold that thought.
Okay. Yeah.
Thank you.
All right. I'll come back to it then.
Okay.
Yeah.
So here I'm just showing you with the actual contours. This is actually computed Lindhard dielectric functions with this anisotropic mass tensor, and you can see exactly the effect I was talking about where the dark matter accessible region is under the orange curve. In one direction you have the plasmon accessible, in the other direction it is not accessible. So you expect a rate difference, and you can actually find a substantial daily modulation for reasonable mass ratios between the heavy and light directions. Okay, this is nice. Now I want to come back to, can we actually find real materials that do this? I mentioned earlier that you can use this whole formalism in an empirical way, in a way that's data-driven. Now I want to make that real. So as it turns out, even though it's hard to go and measure lots of these dielectric functions for lots of materials, there is a kind of intermediate, which is sophisticated computation of those dielectric functions from first principles. So there is a method called density functional theory, which, as the condensed matter folks in the room will know, is highly subject to its own caveats, but nonetheless good for getting some intuition about the structure of various response functions of materials. It can be used to compute epsilon as a function of q and omega. It can even be used to do it anisotropically. And in fact, there is this project, the materials project, that has done exactly that for a very large set of materials. So the materials project has actually studied in total 150,000 materials. They've computed dielectric tensors for about 1,000 of them. So what we've now done is to take those 1,000 materials that are in the materials project dataset, take those dielectric tensors, complete with their anisotropy, and there's a bit of a bootstrapping step. I can tell you more about that another time if you're interested, basically just to make sure we get the momentum dependence right. And I can actually show you now 3 optimal materials for detecting dark matter per half decade of mass. So here, studying all these 1,000 materials, first of all, in the lower panel, these are the best systems just by ordinary dark matter reach, just what's the overall scattering rate in the material. And you can see that there are some very surprising results here. These are not materials that I was ever aware of as someone who's thought a lot about dark matter detection. In the top panel, this is anisotropic reach. This is taking into account how anisotropic the material is and taking into account what we know about the dark matter distribution. At what cross-section would you have enough events to be able to tell that you're seeing the dark matter wind? So that's always going to be weaker than the isotropic reach, but it's the reach at which you can also reject background and actually do something informative. Think about it as discovery reach on top, constraint reach on the bottom. And there's a couple of familiar things up top. Carbon, various forms of carbon have long been known as great dark matter detectors. But what is this? Well, I'll tell you what it is. It's rubidium tetricus zinc triarsenide. I had to learn a lot of chemistry words for this. This is actually a material that's well known, that's been studied a lot for its thermal and electrical properties, that is easily available. You can easily grow it. So it's very feasible to think about making a dark matter experiment out of a material like this. So right now, actually, I'm talking with my friends at the Materials Project to understand which of these materials that we've identified should actually be prototyped in lab. Now, you can actually take this one step further, because I mentioned to you that we have 150-some thousand materials in the data set, but only 1,000 of them have dielectric tensors computed. Wouldn't it be nice if there were a way we could take all the others and just compute dielectric functions for them easily? Turns out there is. As it turns out, there's been now substantial effort in developing neural networks for predicting material properties. And it's actually entirely straightforward to take these tools and take materials from the Materials Project and predict their dielectric responses very rapidly, which means that we can actually bootstrap, use these 1,000 materials to extend to the whole 150,000 material set, and then understand which materials should be then selectively evaluated to see whether we got it right. Now, this is actually so readily available that I can actually show you a preliminary result plot from this. So this is together with a student at Berkeley who's just moving to Fermilab as a postdoc. So here, these are actual, this is not the training set, this is not the validation set, this is the test set. So here we have produced a bunch of dielectric responses from crystal structures, directly from crystal structures. And you can see they are reproducing really, really complicated phenomenology. The bar on the left is showing you basically the distribution of errors. So what it's telling you is that most of the materials in our testing set are really first row materials or second row materials. And there's a few in there that are really bad fits in the bottom row. But even there, it's not going to get you wrong by orders of magnitude. Okay. So now we have tools for very broadly exploring sets of materials for understanding what we should build our dark matter detectors out of. But it's not just about materials. And here's where we come back to those heterostructures. So as it turns out, dielectric response is also modulated by boundary conditions. If I think about a typical dark matter experiment, it usually is some thin layer device at these low masses. So if I actually have thin layers and not bulk infinite volumes, well, what's going to happen to the response function? So as it turns out, this is not that hard to work out in principle. It is very nasty to work out in practice. Essentially, the response of the detector depends on the boundary conditions for electromagnetic waves propagating in those materials. You can actually do this by solving Maxwell's equations. I'm going to skip ahead to the ugly result here, which is that if you solve the Poisson equation for the potential for a given probe charge, then you can write down an effective loss function in terms of that solution that looks like this. So it's messy. And I haven't even shown you here how hard it can be to actually solve Maxwell's equations in some of these scenarios. But even though it's messy, we can still extract a couple of really interesting things. So here's what I'm going to show you. I'm going to show you a thin layer loss function, a set of thin layer loss functions. Now on the horizontal axis is the deposited energy in ratio to the plasma frequency. The vertical axis is the effective loss function. So again, on the horizontal axis, 1 means you're at the ordinary bulk plasmon. And now on the right side, where the plasmon sits at the ordinary bulk plasmon location. This is the limit where the material is a bulk material. So the length scale of the layer is much longer than the inverse momentum transfer, 1 over q. Everything looks normal. But as I go to the left, as I go to shorter layers or to lower momenta, now I move into the thin layer limit, where the layer is no longer large compared to the inverse momentum transfer. And over here you see you have this giant plasmon that has moved to very low energies, which is exactly what you want for a low mass dark matter experiment. You want strong response at low energies. There are a lot of caveats to this story. There are a lot of tricky assumptions on how you actually solve these kinds of Maxwell equations, under what assumptions this actually holds. But the basic result that you move a plasmon towards low energies is quite robust. And actually right now, I am working with a couple others to figure out what are the optimal stacks we can build to actually design the most sensitive experiments. So let's back up for a second. We now have, yeah.
So just as a follow-up to that. So in the optics case, there are scenarios where you can kind of have like an effective medium approximation, right? Where the
Yes.
stack acts like a homogeneous material because, you know, the layer thicknesses are much smaller than wavelength
Yes,
of light.
indeed.
Is that relevant at all?
Yes, yes it is. In
Okay.
fact, that exact limit does happen.
Okay.
And it's just a limit of the wavelength being long.
Okay. Yeah. And what are we talking about in terms of the actual physical dimensions of like the kinds of stacks that you're trying to build?
I'll get there.
Okay.
Good. So I want to back up for a second and just emphasize the key things that we need for a detector before I tell you about actually building one. What we need a strong dielectric response for light dark matter, which means at low energies. We want to get these enhancements from the geometry of the system. We want a low background rate. That's important, obviously. Ideally, we want an anisotropic material. Anisotropic system, really. You can also get this from the geometry. And we also need detectable excitations, the one thing I haven't touched on so far. Right, so detectable excitations, what do I mean here? I mean that, remember, in a direct detection experiment, the idea is that the dark matter causes some transition between eigenstates, and you measure some higher eigenstate. Well, what can you actually measure? In WIMP experiments, this is often something like ionization, right? But in very low threshold experiments, you can't use ionization that has EV or multi-EV thresholds. So I'm going to talk about one of the other possible excitations that you can use here and how that ties into the rest of the story. So I want to now tell you about real detectors that we've implemented in the lab, have actually set constraints with, using superconductors. Superconductors. Here, instead of ionization, the idea is Cooper pair breaking. What does that mean? So in a superconductor, the electrons are bound into these Cooper pairs. There's an attractive interaction that's mediated by phonons in the material. So you end up with this with this condensate of Cooper pairs, and there's actually a gap in the system. There's a lowest energy excitation that's usually of order millieV. That is exactly what we want. That is just the energy it takes to break a Cooper pair. Now, the interesting thing about the actual result of this process, if you actually go through diagonalizing the Hamiltonian, you will find that the new eigenstates of the system are these Bogolyubov quasiparticles. They are effectively combinations of electrons and holes. So the dark matter interacting in the system is not scattering with an electron and making the electron go faster. The idea is actually that the dark matter is interacting with the superconducting vacuum and producing a state of the superconductor that has two quasiparticles in it. The quasiparticles are fermions. They are created in pairs. So this is the process that we're looking for. Now, how would you tell if this actually happened in a superconductor? Well, there are many ways of reading it out. The experiments that I want to tell you about right now use what's called a superconducting nanowire single photon detector, or SNSPD. And an SNSPD, as the name implies, it is nanoscale. These are nanowires. In fact, it's very similar to, if you're familiar with like a transition edge sensor or something like that, it's a very similar idea. So a superconductor has this transition, this phase transition in its conductivity, right, where the resistance drops to 0 below some temperature. This picture is actually just a slice through a more complicated phase diagram that looks more like this. So there's also magnetic field and current that also change where that phase transition boundary sits. So with an SNSPD, you take a wire, a superconducting wire, and you run a current through it. You sit it right at the transition point. So you're sitting just inside the superconducting phase on the current axis. Now, when dark matter comes in, it breaks Cooper pairs. Those Cooper pairs make phonons. Effectively, they make heat at the end of the day. That pushes you up a little bit in temperature. And now there's a spot on the wire if it's not superconducting anymore. So what happens? Well, current flows around the spot. But if current's flowing around the spot, then that means the current density is going up. And so immediately the whole wire transitions to the normal phase. And then you read out this blip of voltage. SNSPDs are great for many reasons. One of the things that's amazing about them is that they can achieve very low thresholds and also achieve very low noise, very low dark counts. And there is one newest experiment on the block, our crocodile experiment. Crocodile is the quantum resolution optimized cryogenic observatory for dark matter incident at low energies. I named it that when I forgot the old acronym we decided on. And it is a next generation demonstrator for an SNSPD detector that's actually sensitive to energy deposits on the order of 0.1 eV. Now, this is a prototype scale device. It is small. It is not yet at the scale where it can probe the interesting cosmological targets. But even being small, it can do some really interesting physics. So we ran it in dark conditions for 415 hours, and we observed 15 counts, which is an extraordinarily low dark count rate. That's really, really good. That actually was enough to set world-leading limits on light dark matter, which I'll show you in a sec. Before I show you those limits, though, I want to come back to the geometry for just a moment. Because to your question, what is the scale of the experiments we're actually doing now? Well, these are nanowires, and indeed, the length scales of the layers are ordered nanometers. Nanometers in my units translate roughly to keV. So if the detector layer here is 2 nanometers thick, I should expect the geometric effects to become important when the momentum transfer gets smaller than a few keV. That in turn translates to dark matter masses of a few MeV, which is exactly the parameter space that's of interest to us. So this is actually the first experiment where those geometric effects are actually important. Now, as it turns out, as you might have guessed, because this effect is anisotropic, it differs based on the direction of the momentum transfer, you can actually get a directional modulation just from having these geometric effects, which means that even though Crocodile was not designed as an anisotropic material system, it is nonetheless an anisotropic dark matter detector. So I'll just show you here. This is the projected daily modulation, effectively, for dark matter of a few different masses in the Crocodile detector. And you see you can get some very large modulations of order 20% or so. Plenty to pick out if you have a large set of events. Based on that, I can now show you limits. Here, this is the standard direct detection plane, mass on the horizontal axis, cross-section on the vertical axis, lower is better. And first, I just want to point out the top of this plot, you should not regard the limits as extending above the top, because then the cross-sections become so large that the dark matter would actually be stopped en route to the detector. So really, it's like a wedge that comes in from the top and down. Now, the blue region, that is the best limit that used to exist, which is actually also our group. And now, the green region is the new limit. And in particular, I want to point your attention to the dashed green curve. That dashed green curve is the region in which we would have had sensitivity to a directional dark matter signal had dark matter been in that parameter space. So we actually already had a directionally sensitive experiment. Now with 15 events, there's not really any point in doing a directional search. We did it anyway, just to satisfy ourselves. But that is sort of the thing I want to make clear here is this gap between the bottom of the green region and the dashed green line. That gap of an order of magnitude or two, that's just telling you you need 10 to 100 events in order to see the directionality. Now, a few other curves here. The orange curves are projections for future experiments. So first of all, if you take this exact device and you just make 10 million copies of them, then you would get to this dashed orange line if you didn't have any background, and if you coupled that with some new technology that we have in the lab that reduces the threshold further. Now you would say, how realistic is it to have 10 million of these things? Well, I've got 10 million sensors on this. Not that hard. It actually is, there are significant challenges to these kinds of scaling problems, but it's not like you have to do everyone by hand, right? The idea is to basically make a camera chip, very, very similar to CCD pixel arrays. So that is actually realizable. In fact, there's already an example in literature of someone making a 100,000 scale array of these devices. Now, I mentioned we have a new device that has a lower threshold. That lower threshold, if we can achieve it for that futuristic array, actually allows us to go down almost to the keV scale. We're really only now about one order of magnitude away from the sensitivity that we set out to reach at the beginning. I also want to point out that the dotted orange line is kind of unrealistic. Why is it unrealistic? It's not because of scaling. It's not because of threshold. It's because of background. We know there are backgrounds. We know that there will be backgrounds that we don't know of today. We don't know how they scale. But we do know that we have directional sensitivity. And with directional sensitivity, it is possible to scale the sensitivity of the experiment as the square root of the exposure, even if you have an unknown background present. So that is going to be the silver bullet towards getting to those low cross sections. Ultimately, the cosmological target we want to achieve is right around where the dotted orange line sits. Okay, I want to just say one more preview of where this is going before I wrap this up. So as the one last thing, everything that I've been talking about so far is about dark matter scattering with electrons, which is all well and good. But you could say to me, what if dark matter doesn't scatter with electrons? What if it only scatters with nuclei? As it turns out, exactly the same systems that I have been telling you about can be used to study dark matter nuclear scattering. Now, why is this? I gave you this nice argument before that the target mass for a nucleus was way higher, so you weren't sensitive to low mass dark matter. But in this parameter space, at these low energy transfers, you aren't seeing individual nuclei. You're seeing collective excitations. So you're talking now about producing phonons, right? Vibrations of the nuclear lattice. And those can be much lower energy. So in fact, if I have dark matter coming in and scattering with electrons in the system, I actually inevitably produce these kinds of phonon final states. In fact, generically, as it turns out, I'll end up with about half of the energy in the final state being in the form of phonons. So even when dark matter interacts with electrons only, I end up with half of the energy in the nucleon system. So if that's the case, surely if I scatter directly with the nuclei and do the same thing, I can hope to achieve similar sensitivity. So we actually computed this from first principles. We computed the rate at which you excite phonons in a material. We used density functional theory to come up with the actual phonon spectrum for different materials. And based on that, we are actually able to set limits on dark matter scattering with nuclei. This is the plot that appeared in the first paper where we figured out how to do this, but I actually want to show you this version here, which takes advantage of the crocodile experiment, that latest SNSPD experiment. And you can see that that green line is now moving below in mass where all of the traditional experiments are able to probe. You might notice as well, it's a bit hard to see on the screen, there's this other portion of this curve called migdal that extends all the way out to about 1 MeV. And it looks like that can get to quite low masses just using traditional tools. So what's that about? Why is that doing so much better? Well, the Migdal effect, which is what that curve is showing, that is when dark matter scatters with a nucleon, but immediately transfers all the energy to an electron orbiting it. So you kick out the electron, that means you have the kinematics of electronic scattering, even though you have a nuclear interaction. That's why it goes down to the MeV scale. As it turns out, there should be an analog of the Migdal effect in superconductors. It's this diagram. It's when the dark matter comes in, scatters with a nucleus, makes an off-shell phonon that then produces quasiparticles. So right now, a student of mine is hard at work computing exactly the rate for this process, but it should actually be able to extend similarly. Just as the traditional experiments get this enhancement from Migdal, the superconducting experiments should also get that enhancement. Okay, I want to wrap it up here. I just want to leave you with a few thoughts. First of all, that dark matter detection is broadening tremendously from where it started. It is no longer big tanks of xenon waiting for dark matter to scatter. We are now taking advantage of condensed matter tools in particular to be able to broaden our sensitivity to particular classes of dark matter models. We are actually taking advantage of the data that has been assembled in the condensed matter world to design optimal detectors that are sensitive to all the dark matter phenomenology that we want. And these ideas are being actively prototyped in real experiments so that it is entirely reasonable that on the 5 to 10 year time scale, we will have exhausted the program of light dark matter detection. And we will know if dark matter is a light fermion produced by these cosmological processes. I'm going to stop it there. Thanks, everybody.
In your crocodile chip, once you quench one of your superconducting circuits, then it'll go resistive. It'll heat up for a short time, and then it'll cool down again and get into a superconductor. But it won't have any energy anymore. Do you have like an inductive supply to rev it back up again, or do you just leave them down until the experiment's over?
No, it is coupled to a big inductor indeed. Okay. So yes, it is a very short dead time.
Right.
But
okay.
Yeah.
And just as a note, my first time I was on this campus was in the summer of 1968 as an undergraduate when I did computer simulations of quasi-particle theory using Fortran and punch cards.
I would like you to know that one of the first things I did as a grad student was doing simulations of quasi-particle dynamics in superconductors. I was doing it for anisotropy purposes, but without Fortran, I'll say.
Yeah.
Yeah, I was wondering, you said you were projecting you could make 10 to the 7 detectors. Is there a reason why you stop there? Why not a billion or something?
Yeah. So even though it's in principle possible to fabricate these detectors at scale, the real challenge is in multiplexing the readout. It is not trivial to actually be able to address all of these devices simultaneously. It has been demonstrated, but that 10 to the 5 demonstration is actually fairly recent, and we don't exactly know how it's going to scale to the low threshold devices that we're using. So I would say we just don't know how feasible it is to scale beyond that. In principle, there is a real target. Like, I don't want to arbitrarily go higher, right? In fact, one of the questions that I often ask myself with direct detection is, when do you stop? Right? You can always build a more sensitive detector. When does it stop becoming the thing that you should do to look for dark matter? Well, I would argue that it stops becoming the right tool to look for dark matter when you have exhausted the reasonable cosmological targets. And as it turns out, the reasonable cosmological targets that you can probe with these kinds of devices, you can certainly probe those with order grams of detector. So here, I'm talking about, typical detectors are maybe micrograms, right? So yeah, 10 to the 8 is sort of what you need. I don't need a billion necessarily. But I wouldn't, if you gave it to me, I wouldn't say no.
Thank you. I really enjoy. I hope that the dark matter talk to the electrons because really.
Indeed, me too.
Just one comment, just for the students. I don't want to go in controversial discussion, but this name of WIMPs has been used for a long time, and people should think about that like kind of a benchmark scenario. But you can build so many things that even a window and all the things that, you know, they have even weak interaction, but they are suppressed because they are low level, and, you know, many technical things, right? But it's important to see. I think, in my opinion, we should explore every possibility because we don't know what the matter is, okay? The second thing is about Cocodrile. Every scenario that you guys have, how ambitious you guys are you assuming toy models to reproduce the Rayleigh density? Or you say, oh, I get Rayleigh density somehow, but I am only interested in constraining the cross-section in that regime?
Good.
How much model dependent can you guys avoid, let's say?
Good, good. So I first actually want to speak to the first point you made about WIMPs, because this is a question that I discuss with people often. If you are in doubt about WIMPs, you should come to Thursday's talk. Because WIMPs are very much alive and well. They are a very broad category of particle. People disagree on how to even define what they are because the category is in fact so broad. In fact, I think that the definition that I tend to go by, that I think a lot of people agree on, is that anything that has a roughly weak scale mass and cross-section that is produced by thermal freeze-out or something like it is WIMP-like. And that's actually a very broad category of physics, some of which definitely cannot be tested by direct detection. And some of which actually will probably not be tested for a long time. To the second point, on crocodile, would you remind me of the...
Basically, as you know, depends how much
model
independent
yes.
you want.
Good. So indeed, if you look at the actual constraint that we have set here, right, that's at fairly high cross sections. It's at cross sections that are, in principle, could I model build something that lives there? Yeah, you can do something tricky, but you have to do something tricky.
Right, that's my point.
Exactly. So I'm not really even interested in saying, here's a set of models like it, because that's it's almost a trivial exercise, right? My PhD advisor, whom you know, used to quote what he called Redmond's theorem, which is that any competent theorist can fit any given set of experimental facts to any given theory. So I want to avoid that. I want to say there are real interesting targets to go for. We might get really lucky and discover something really exciting that happens to live at higher cross sections. Maybe dark matter, does an entropy dump, and that means it doesn't need that cross section. Maybe dark matter goes through a phase transition and then has a much higher cross section today. Maybe there are enhancements because of cosmic ray boosting that mean that you actually see things earlier than you would expect. So it's not that, I think that dark matter probably lives in this space. I see this as a step towards probing the models that are actually qualitatively interesting, and if we happen to get lucky, that'll be great.
Can you show the plot where you have prediction for the Dirac materials? I personally like a lot of Dirac materials. They was very competitive when, let's see, you have...
Are you talking about...
Yeah, you were showing the different possible bounds from the... even previous.
Earlier?
You remember you have a line that is very competitive using Dirac material. I guess you are using some of these...
Well, I think that I only bring up... Dirac materials are basically one way of getting a low Fermi velocity, so I don't think I had them before here.
But they're fascinating, and you can fine-tune them.
They are, but they're also hard to fabricate. So I don't really know what the long-term prospects are for using them. You have to fabricate them at scale, right?
You can do the thing.
Exactly. Yeah. There are proposals for large, graphene systems like Ptolemy, right, doing like cosmic neutrino detection. And if you are lucky enough to have an experimental platform that is so constructed, you can probably use it to do dark matter detection at the same time.
Yeah, the Italians are doing that, I believe.
When you were showing all of these dielectric functions you calculated from the materials project, I was wondering, are most of these metals or are they insulators, semiconductors?
They're all over the place. So the materials project, they are trying to just study all of the.
Yeah, but the ones that you found are useful. And
Oh,
when you're
actually-
calculating the dielectric functions in a semiconductor, it's pretty straightforward because it only involves interband transitions. But in metals, you always have this Drude kind of term which is diverging, and it's more tricky to calculate it.
Indeed. And actually, I don't know of these materials which are semiconductors and which are insulators, and I don't actually know that for these materials. It does. I just haven't looked at it. But if you right, that's the thing, is that because materials project is predicting all of these things from DFT, and DFT famously doesn't get things like gaps right for all materials, right? So actually that's So one of the things, for example, that Bethany and I have been trying to do in this piece over here, where we're doing neural nets to predict dielectric functions, we are trying very hard to see if we can actually reduce the dependence on things like the gap that materials project computes, because we don't know if we trust it. In fact, even this plot here, this is a somewhat earlier version of the plot, actually before the paper appeared, because we realized that there were some non-trivial aspects to how the gaps were handled in the materials project, where there are actually several different gaps they compute and the different methods. It's kind of complicated, and we had to end up tweaking things a little bit. This is the version for a talk, so it's already made nice, but if you look in the paper, you'll see a slightly different version.
Here's a question.
Please.
You shown many phase diagrams, but as far as I understood, the main excitation you're looking for is within the milli-EV regime, the electronic response. There are other excitations, quasi-particles within the regime. How
Yes.
do you exclude?
Yes, absolutely. So let me say first of all that really what we care about is any excitation milli-EV or above, right? So I'm not saying that I can't use something that's higher. It's just that I want to be able to get down that low, so it helps to have a gap that's milli-EV or lower. So there are plenty of other excitations. So for example, one of the other candidate systems for doing this kind of low mass direct detection is superfluid helium, where there are quasi-particles in that system. There are also things like rotons, and there are magnons. There are other kinds of quasi-particles that can be used. Some of them are better suited to certain interaction structures. So for example, if you have a spin-dependent interaction, everything I was talking about here was on the spin-independent side, right? If you have spin-dependent interactions, that couples differently to those excitations, and so you want to use the ones that are spin-coupled. Yeah, for these purposes, at least for the superconductors that are being used in crocodile, for example, we are pretty confident that we're limited to those excitations, just because we know those materials. But in principle, yeah, you could have a whole forest of quasi-particles to deal with.
Right, if there's no more questions, let's thank Ben again.